Welcome to The Explainer. Today, we're diving into a real cosmic crime scene. One of the biggest mysteries in all of science, the case of the runaway universe.
So, for almost 100 years now, we've known this one basic thing about our universe. It's expanding. It's getting bigger. Every galaxy is moving away from every other galaxy.
And for a long time, we thought, okay, this makes sense. You've got gravity, right? This giant cosmic brake pedal that pulls everything together. So naturally, scientists figured it must be slowing that expansion down. It just seemed logical.
But then, 1998 happened. You've got these two teams of astronomers, and they're staring at these incredibly distant exploding stars, supernovae. They were looking for proof of that slowdown. But what they found? Oh, it was the exact opposite. The universe isn't slowing down. No way. It's actually hitting the gas.
Can you imagine? This one discovery just completely flipped the script on cosmology. It basically opened up a cosmic crime scene. And that's what we're doing today. We're going to investigate the prime suspect, this mysterious thing we call dark energy.
Okay, so to get to the bottom of this, we need to look at the evidence. What was the clue that first pointed us in this direction?
So the culprit, this thing pushing everything apart, we've given it a name, dark energy. And here's the crazy part. This isn't some small background effect. No, it makes up something like 70% of the entire universe. All the stuff we know, stars, planets, you, me, that's just the tip of the iceberg.
All right, so how do you even start to tackle a mystery this big? Well, you start local. Cosmologists began by trying to measure the expansion rate right here in our own backyard, dusting for fingerprints at the immediate crime scene.
And they have this really clever method for it called the cosmic distance ladder. It's exactly what it sounds like. You build up your measurements step by step. First, you get super precise distances to nearby stars. Then you use those stars to figure out the true brightness of other special stars called Cepheids. And then you use the Cepheids to measure the distances to those super bright supernovae way, way out in the cosmos. It's a brilliant step-by-step process.
So, after all this painstaking work, what do they get? They get a number for the expansion rate, what we call the Hubble constant, and that number is about 73. So what does that even mean? Well, for every 3.25 million light years you go out, a galaxy is flying away from us 73 kilometers per second faster. And you'd think, great, we've got our number, case closed. Yep, not so fast.
Because see, a good detective never relies on just one piece of evidence. You always look for collaborating witnesses. And the next clue? It comes from somewhere totally different, from the very beginning of the universe.
This is the cosmic microwave background, the CMB. You can think of it as the afterglow of the Big Bang. It's literally the universe's baby picture, a snapshot of what everything looked like when it was only 380,000 years old, and that picture is packed with clues.
See, baked into this ancient light are these tiny little hot and cold spots. They're like leftover ripples from sound waves that were moving through the super hot, dense baby universe. And because we understand the physics of that primordial soup really, really well, we know exactly how big those ripples were back then. It's like having a cosmic standard ruler, a measuring stick of a known size from the very beginning. Okay, so here's where it gets wild. We can take that standard ruler, that known size from the baby universe, and use our best theories of physics, our standard model of cosmology, to predict what the expansion rate should be today. It's like a forecast. And the number that forecast spits out, it's about 67. Wait a minute.
And Houston, we have a problem. That's not a small difference. That's a real disagreement. We have two completely different, totally reliable methods of measuring the universe, and they are giving us two different answers.
So let's be clear. The number we measure right now using stars and supernova, the late universe measurement, is 73. The number we predict based on the baby picture of the universe, the early universe model, is 67. The fingerprints at the crime scene just don't match the DNA evidence. They're telling two different stories.
And this isn't some tiny error that'll go away with better telescopes. Actually, the better our measurements get, the worse the problem seems to be. This is a full-blown crisis in cosmology. It has a name, the Hubble tension.
And you have to understand, the stakes here are enormous. This isn't just about a number. This tension, it's like a crack in the foundation of our entire understanding of the cosmos.
It's screaming at us that something is missing from our story, or maybe that the story we've been telling is just plain wrong.
So what do you do when your main theory doesn't fit the facts? Well, if you're a good detective, you start looking for new suspects. And right now, scientists are throwing some really wild ideas out there. I mean, what if our understanding of gravity is just wrong over huge distances? Or maybe there are new, undiscovered particles messing with things. But out of all these ideas, one in particular is starting to look like a really strong contender.
It's a concept called early dark energy. The theory goes like this. What if, for just a little while, way back in the early universe, there was another kind of dark energy, a temporary boost? If that happened, it would have ever so slightly changed the physics back then, and it would mean our standard ruler from the CMB was actually a little bit smaller than we calculated. And if you rerun the numbers with that smaller ruler, poof, the prediction from the early universe lines up perfectly with the measurement from today. The two clues suddenly match.
But hold on, this case is anything but closed. This is a live investigation. Seriously, new data is coming in right now that could change everything.
We've got this whole new generation of incredible telescopes on the case. You've got the James Webb Space Telescope, which is giving us these stunningly sharp images of those key Cepheid stars. Then you've got the Simons Observatory, which is going to look at that CMB, that baby picture of the universe, with insane precision. And then there are missions like Euclid, which will map out billions of galaxies to create this amazing 3D map of the cosmos. All this new evidence, it could be the thing that finally cracks this case wide open.
So that leaves us right here, on the edge of a massive discovery. Are we about to find a whole new law of physics, a piece of the cosmic puzzle we never even knew was missing, or have we just been reading the clues wrong this whole time? That's the question that astronomers are racing to answer. Because the Hubble tension isn't just a problem, it's a clue, and it might just be pointing the way to a revolution in how we see everything. The investigation is still very much open.